Picture this, you're building a motion tracking wearable and your ESP32 needs to constantly stream data from an accelerometer while also driving a small OLED display. If you tried wiring each sensor pin directly, you'd run out of pins in no time. That's exactly why protocols like I2C and SPI exist. They're the shared languages that let your ESP32 communicate with dozens of devices over just a few wires. In this lesson, we'll unpack how these two protocols work, when to use each, and how to actually hook them up in real projects. By the end, you'll be able to confidently connect and test devices like the MQTT motion sensor and SSD1306 OLED, avoiding the common mistakes I see juniors run into every week. Think of I2C as a single neighborhood street with houses on either side. Each device has its own address, and the mailman, your ESP32, walks down the road delivering data to whichever address he calls. With just 2 lines, SDA and SCL, you can connect multiple devices like displays and sensors, each responding only to its address. On ESP32, the defaults are SDA on GPIO21 and SCL on GPIO22, but unlike older boards, you can remap them if needed. This flexibility matters in real builds where pin conflicts happen often. The beauty of I2C is its simplicity. No matter how many devices you add, those 2 wires don't change. The catch? All devices share the bus, so speed is limited, but for most sensors and small screens, it's more than enough. Now, SPI is more like a multi-lane highway, where every car has its own entrance ramp. It uses 4 main lines: MOJI, MISO, SCK, and CAs. Data flows fast, often 10 times faster than I2C, which makes it the go-to for displays, memory cards, and high-throughput sensors. The ESP32 usually maps MOJI to GPIO23, MISO to GPIO19, SCK to GPIO18, and CAs to GPIO5, though you can adjust these. The trade-off is wiring. Each new device needs its own chip select line. I've had projects where running too many CAs lines became messy, and in those cases, I2C was easier. But if you care about speed and stability over longer runs, SPI wins every time. Think about your project. Do you need fewer wires or higher speed? That choice defines which protocol to use. Here's a direct comparison that helps you decide quickly. Look at the wiring column, 2 wires for I2C versus 4 + 1 CAs per device for SPI. Then notice the speed difference. I2C tops out around 1 MHz, while SPI can run at tens of megahertz. If you're adding multiple sensors with limited pins, I2C is your friend. If you're moving lots of data fast, SPI is the tool you reach for. I often start with I2C for prototypes, then switch to SPI if performance becomes a bottleneck. Use this table as a mental shortcut when planning your next project. Let's get hands-on. Imagine wiring both an SSD1306 OLED and an MQTT accelerometer to the ESP32. With I2C, both share the same SDA and SCL pins, so wiring is neat. OLED SDA and MQTT SDA both go to GPIO21, while both SCL pins go to GPIO22. Power each with 3.3V and GND, and you're done. Next, you run a simple I2C scanner sketch to confirm devices are alive. The OLED should respond at address 0x3C and the MQTT at 0x68. This scan is your first sanity check before you touch display or sensor libraries. It saves hours of head scratching by confirming the wiring and addresses are correct before diving deeper. This code is an I2C scanner for the ESP32. Before using any I2C sensors or displays, it's a good practice to scan the bus and confirm their addresses. The code begins by initializing the I2C interface on pins 21 for SDA and 22 for SCL. In the loop, it tries every possible address from 1 to 126. If a device responds without error, the address is printed on the serial monitor in hexadecimal. In the sample output, we see 2 devices: the OLED display at address 0x3C and the MPU6050 sensor at 0x68. If no devices are detected, a message is shown. The scan repeats every 5 seconds, ensuring your I2C peripherals are correctly connected and active. This code demonstrates how to drive an OLED display with the ESP32 using the Adafruit SSD1306 library. First, the display object is created with a resolution of 128 by 64 pixels. In the setup, the display is initialized at I2C address 0x3c. If initialization fails, an error is printed and the program stops. Once the display is ready, we clear the screen, set the text size to 2 for bold letters, and choose white as the text color. The cursor is positioned at coordinates 10, 20, and the message Hello IoT is printed. Finally, the display command pushes the text to the OLED screen. The loop is empty, since we only want to show this static message once. This program reads acceleration data from the MQ6050 sensor using the ESP32. First, the Y library is initialized for I2C communication, and the MQ6050 object is created. In the setup function, the sensor is initialized and its connection is tested. If successful, the serial monitor confirms that the MQ6050 is connected. Inside the loop, we declare 3 variables for acceleration along the X, Y, and Z axis. The function getAcceleration fills these values, which are then printed to the serial monitor. The Z-axis value is typically close to 16,384, representing the constant pull of gravity. The readings update every half a second, allowing you to observe how the accelerometer reacts to movement and orientation changes in real time. Here's where most beginners stumble. First, swapping SDA and SCL, double-check your pin mapping, especially on boards with different silkscreen labels. Second, missing pull-up resistors. Some modules have them built in, some don't, and without them, the bus won't work reliably. Third, power mismatches. Feeding 5V into a 3.3V sensor will silently fry it. I've seen it countless times. On SPI, the classic mistake is forgetting unique chip select lines, which causes devices to clash on the bus. And when a device locks the I2C bus by holding SDA low, a quick reset usually fixes it. But in production, you'll want a recovery routine. Debugging always starts with the scanner sketch. If the device doesn't appear, focus on wiring and power before suspecting libraries. The best way to cement this knowledge is by building something small and functional. Try reading acceleration from the MQ6050 and printing stable or moving on the OLED based on motion. Or attach a BME280 sensor and show temperature and humidity on the screen. Suddenly you have a pocket weather station. If you want to see the wiring difference, swap the I2C OLED for an SPI version and measure performance changes. And for a challenge, connect both the MQ6050 and the BME280 on the same I2C bus to confirm multi-device operation. Each mini project reinforces not just coding, but also wiring discipline, scanning, and debugging, all critical habits for professional IoT builds. By now, you've seen how I2C and SPI aren't abstract protocols but everyday tools you lean on in nearly every ESP32 project. You know how to wire them, how to scan and validate devices, and when to pick one protocol over the other. These skills scale directly into real projects, from wearable trackers to smart displays to storage-heavy IoT gateways. Each time you add a new device, you'll approach it with confidence, knowing how to debug wiring, confirm addresses, and avoid the rookie mistakes that slow projects down. This lesson gives you the foundation to expand your ESP32 beyond simple GPIOs into full sensor networks and rich peripheral systems.